Hello, everybody. It's 3 p.m. on the third Thursday of October. A very warm welcome to the 14th edition of our 3D Thursday webinar series. It's fantastic to see so many passionate professionals joining us today as we dive deeper into another very transformative topic. The topic for today is From Particle to Part, the science and strategy of metal AM powders. In this session, we will provide a brief introduction to metal AM powders covering different atomization methods, key terminologies, and common sources of defects in powder. We will also discuss important powder quality parameters that impact the AM part performance, as well as M4P's approach to monitor these quality parameters. Finally, we'll offer a glimpse into the future of metal AM, including new materials specifically designed for additive manufacturing. We encourage you to actively participate during the session. While we will have a dedicated Q&A session at the end, our speaker today, Mr. Priyanshu Bajaj, he might take some of your questions as and when they come in. So keep submitting your questions via the chat feature. I repeat again, please feel free to submit your questions via the chat feature. To make sure we cover as many queries as possible, we may group similar questions together. Please note, today's webinar is being recorded for educational purposes. By being here, you agree to the session's recording and distribution within our learning community. It's now my pleasure to introduce today's expert speaker, Dr. Priyanshu Bajaj. He is an expert in metal additive manufacturing with over 10 years of experience in the industry and research. Currently serving as Regional Manager, Asia Pacific at M4P Material Solutions, he specializes in addressing material challenges in additive manufacturing. His work goes beyond traditional AM materials. He helps in developing new materials for AM and also developing process parameters and other post-process heat treatments specifically for AM materials. Prior to his current role, Dr. Priyanshu Bajaj was a doctoral researcher in additive manufacturing at Max Planck Institute for Iron Research. He holds a Doctor of Engineering in Metal Additive Manufacturing from RWTH, Aachen University, I hope I said it right, and a Master of Metallurgy in Advanced Metallurgy from the University of Sheffield. Throughout his career, Dr. Priyanshu Bajaj has contributed significantly to advancing material solutions for metal AM and continuing to drive innovation in the field. We're privileged to have him share his deep insights and innovations with us today. So, Dr. Priyanshu Bajaj, the floor is all yours, and I will be back to moderate the Q&A session.
Thank you very much, Akshita. It is a pleasure to be here. I've been following the 3D Thursdays for a while now, so it's a pleasure to be on the other side for a change. Thank you, Wipro, for setting it up. I think it takes quite a lot of work and commitment to do this week after week after week. So thank you, Manoj. Thank you, Akshata, for setting this up, giving us your time. I will now share my screen if it's okay.
Yes.
So with this amazing introduction and background, let us get directly into it. From particle to parts, this is a brief, let's say, starts from the history to a bit peeking into the future of what metal powders could look like, specifically when it comes to additive manufacturing. Before that, I'll give a short introduction to M4P. M4P stands for Metals for Printing, and as the name suggests, we make metal powders and only for additive manufacturing. This is sort of what differentiates us in the market, uh, where we have many metal powders companies, but I think there are very, very few, if not the only one, who do metal powders only for additive manufacturing. And you will appreciate this more as we go along this today's topic. Um, just a brief history. We were actually founded in a garage of some of like HP and so on in 2015. So this year we complete our 10-year anniversary in the very small town of Magdeburg, close to Berlin in Germany. As a company, we like to see ourselves as a materials company. So it's all about materials. In a short team, we have quite a number of PhDs and masters, which goes with the nature of the business that we do. So it's all about powders. It's all about materials. What it means is we define our own chemistries, even when it comes to standard powders. We define how to control them, and going beyond how to process them in 3D printing or AM, and how to do post-process additive manufacturing and so on. The whole concept is also like AM because we understand time is critical. Time is in many ways the defining factor why you would want to go for AM. So everything is very, very fast. We work in one point of contact principle, meaning you have one point of contact, and this person has the visibility of the entire chain. So stock, delivery, supplies, R&D, technical data, everything. Materials can be shipped to you in 2 to 3 days from order. Uh, all of this combined made us one of the top powder suppliers for AM across Germany and even India now. Um, and this includes the entire chain, so from end users to machine OEMs to R&D labs across families. So be it aluminum, steel, nickel, and across machine types. So we support all major machine types. And yeah, this is what sort of defines us. Our offerings, the biggest one, of course, is metal powder, bread and butter, but then we do all of it. And I think today is a glimpse of some of the other things. So, AM training, AM outreach, this is one of our offerings. Of course, today for Wipro, we are doing it in a similar fashion. This is our portfolio in brief. For those of you new to AM, I think for those who are practicing in AM would already recognize that this is one of the widest AM ready materials portfolio. Most of these materials are on stock, can be shipped immediately, and for many of these, we can even support you with starting process parameters. And you will see this is across families, aluminum, coppers, a very, very wide variety of steels, nickel, titanium, so across machine types and so on. Now, jumping right into our topic for today, metal powders. Let's start with a brief history. So, powders are actually not new. AM is new. AM is around 1990s. The first instant of 3D printing, you can imagine metal 3D printing at Fraunhofer ILT in Germany, in Aachen actually. Um, but powders is not new. This is a piece from 800 to 100 BC, and you already see it has pieces or particles of powder onto it. So at least powder existed then. Of course, these are quite coarse compared to the powders that we are talking now, but then it's also gold, yeah. Uh, so if you look around, we have many kinds of powders in the past in history. You have gold, of course, but then you also had powders of lead, tin, zinc, aluminum in 19th century. Different forms of methods of production, sputtering, and so on. Uh, very close sort of atomization. This is maybe the closest to how we produce powder today for AM. But as such, powder is not new. Uh, and many of the principles remain the same. Looking at how the powder market is globally, this is in tons per year, and you see the trend. Iron, of course, is the biggest one. Then you have zinc, aluminum, and so on. This is not the full picture, though. I mean, if you look at it, almost a major chunk is conventional powder metallurgy, and then you have explosives, your firecrackers and so on. Diwali is coming, so all of these firecrackers they have metal powders in it. AM, unfortunately, is a very small fraction of this market, and this is uh, really the market where we are playing. So we focus on really. I think today it's around 2% of the market. It has grown a bit. This is from 2016. Today, this number is around 2%. So 2% of total metal powder market is metal powders for AM. And this is the market where we are operating. And this is how you can sort of guess or judge the specialty that we operate with. Then you have, of course, different methods of making powders. So you have mechanical methods, you have dry reduction, wet reduction, electrolysis, and then you have a lot of carbonyl, decarbonyl, and so on. Most of these are not suitable for powders that we need for AM. Because of course for AM we need powder which can flow in the machine, which can spread in the machine, and this means this powder has to be spherical. Has to be flowable, and unfortunately many of these methods do not produce powders which are fit for use in AM. And which brings us to methods where you can make spherical powders. So all of these methods, you can make powders which are spherical and which you can use in air. Again, you will see this is also not one method to make powders. So you have many different methods here. The first one, from left to right, the quality quality of the powder increases, but so does the cost. So on the leftmost, we have open melting. So powder is melted in an open furnace, and then you have atomization happening. It flows down a nozzle, gas is applied at pressure, and you get metal powders. Not so nice powders in terms of purity because, of course, it's open to atmosphere. You get some oxides, you get some slag particles, and so on. But when you are looking for something very cheap, something for architectural use and so on, you can use it. Then you have Vega. Basically, the melting unit is under vacuum here, and the melting is done under a protective atmosphere, maybe an argon or nitrogen gas. And then you have the crucible that tilts into the nozzle, and of course, gas comes and you atomize. Um, More pure powder, slightly larger batch sizes. Uh, Over a period of time, the PSD range is a bit wider. Then you have Vega, which is bottom pouring crucible. So there's a hole at the bottom of the crucible. You you have a plunger, you pick it up, and the powder goes. The liquid metal flows down. Difference between this and this is that this is much smaller units. Because they are smaller, you can control the chemistry more precisely, you can control the PSD more precisely, but essentially the same principle. Then you have electrode induction gas atomization. Here you don't have a crucible because when you have a crucible, you still have a chance of the metal interacting with the crucible and forming all sorts of nasty things that you don't want. Think reactive metals like titanium, magnesium, or materials where you want them to be pure copper. You ideally would like to avoid a crucible or anything touching your liquid metal. And this is where IGA comes into picture. So you have an electrode, a rod uh, with a V with a conical shape at the bottom. You have induction coils. Because of the coils, you get melting on the skin of the cone. And this flows down to the nozzle. Again, the same principle. You pass gas at high pressure. This could be argon, this could be nitrogen, and you get metal powder. Then we have plasma. Here you have a wire. So only for materials where you can form a wire in titanium, copper, etc., etc. The wire is passing through a plasma torch, which melts it, and then you have again the same principle, gas coming in at high pressure, which forms the powders. And lastly, you have prep. The wire is replaced by a rod, a rotating rod. Again, the same principle. You apply plasma torch, and the rod is rotating at a high pressure, and then again you have gas coming in to make powder. So left to right, your uh, powder quality, if you can say, will increase, and we will come back to it later what we mean by quality, but so does pricing. In between, we have something called as plasma spheroidization. This is where you can take slightly non-spherical powder and pass it through the plasma torch. What happens here is when you're passing the powder through a plasma torch, the outer layer of the powder is melting and is resolidifying. So over multiple cycles, 2, 3, 4 cycles, your irregular shaped powder will slowly and gradually become more spherical and more spherical and more spherical, ultimately into something that you can use in AM. Keep in mind that the chemistry does not change and the size does not change. Only the shape or the morphology of the powder is changing in this process. So you can use it for recycling. You can use it when you have a non-spherical powder source. You can use it for that. Uh, Moving on, we have now what is powder and what are the different terminologies. So let's say morphology. Morphology means the shape of the powder. Is it a sphere? Is it like a football? Is it like an oval, like an American football? Is it very irregular shape? Is it disc and so on? That's called morphology. Then we have purity. Purity is the chemical composition, the purity of the powder, gaseous content, your things that you do not want in your chemical composition. Could be, let's say, copper in a nickel powder, things like that. Feasibility, meaning can we make a powder out of it reliably, batch after batch after batch. So not everything can be made into a powder. That's key. Yeah? So it's easy to assume you can make powder out of anything, but that's not true. You have to think about how it interacts with the crucible, how it is interacting on atomization, and so on. Distribution and yield. This is the size distribution. So when you're making powders, you get everything from 0 micron to 200 to 50 micron. So distribution is basically that bell curve. What is the size fraction, what is the size distribution of the powder, and yield is different processes, different AM processes use different PSDs. So laser powder bed, you need, let's say, 15 to 45 or 20 to 63 micron. Binder jetting, you need minus 32 micron. DD, you use 45 to 90, 45 to 106, 45 to 150. Electron beam, you're using 45 to 106. So yield is basically the size you are using versus everything that you produce. Normally, it's about 3% for AM. Homogeneity is how homogeneous is your powder, as the word says, and this is in two ways. One is with respect to particle size, shape, morphology, size, and another is chemical homogeneity. How identical are two powder particles with respect to chemical composition? You don't. It's why the changes could be because let's say you're melting and the powder, which is atomized at a later stage of atomization, has more time to react with the refractory. In that case, you will have some sort of inhomogeneity in the powder. Going more into morphology, this is what it means. Different shapes, yeah. Left to right, our quality is decreasing. The powder is becoming less suitable for use in AM. What you need, what you can process, does not always has to be this. It can be this, it can be even this in some cases. It depends on what machine system I'm operating, what I can live with. Ultimately, my aim is to make a component out of the powder. It is not to take a picture and hang. So if I can work with this or this, it's good enough. You don't always have to have this because there's a cost associated always to go from here to here. So we have to look at what machines we are operating, how well different machines can handle it. So there are machines where you have powder in a beaker, and this is coming down, and then this is spreading. So here you need flow down flowability and then spreadability. These machines normally have lower tolerance for irregularity versus other machines, you have powder in a beaker, this is lifted up and you only have to spread. Here you can have a little bit more tolerance when it comes to flowability. Then you have some very special machines where powder is even sucked out and is recirculated back. Here you have even lower tolerance when it comes to morphological differences. Now coming to how is a morphology defined, or where is the culprit when you get the bad morphological powders. So how is a powder made? Basically you have a stream of metal. You bombard it with the gas, argon or nitrogen. You break it into a melt droplet. Given enough time, any droplet of liquid, be it metal, be it water, would make a perfect sphere. But we have to cool it down. So the quicker you cool it down, the poorer the morphology, basically. The slower the cooling, the better the more spherical the powder you will get. Counter side is the slower you are cooling, you will get coarser particles and so on. So there's always a balance you have to maintain. Water atomized particles, for example, will always be very, very poor in terms of morphology because it just cools so fast. It does not sterilize, which is why gas atomizer is what we normally use in it. Again, the pressure, the temperature, and so on plays into the morphological aspect of the first degree. These are the different parts of atomizer. So again, this is where you are melting. You make a stream of the metal. You have a nozzle. In some atomizers, this is clubbed with the tundish. So you have both together. This is called a closed loop nozzle. And here is when you're breaking it into particles and you're making powder. So step one is basically you have a stream, initial stream of powder, then you break it into smaller fragmented stream, and finally this is what you're making into small powders. So this is primary atomization, but remember the particles are still soft. And you can have a case where the gas is then coming back, is flowing back, and the small particles are going and are welded on top of the bigger particles. This is what we call as satellites. So you have a big particle and then small particles on top of it, welded on top of it, or sticking to it. This is where you have what you would call as a satellite. Again, very bad for flow, cannot be avoided fully, but there are methods you can imagine. Now that you know what is causing, you have a circular flow of air, and this is what is causing satellites. So imagine if you want to prevent it, you can have more top pressure, you can have cyclones, so taking away fine particles and so on. This is how you would normally avoid satellites or reduce satellites. Similar with coalescence, So there are some things which are avoided at the time of designing of the atomizer. So if you want to have top pressure, you need to have hardware for that. If you want your cooling rate to be low to make more spherical particles, you need to have hot gas. So you need to heat the gas which is entering. So for this, you need to have a heating system. And then there are things which you can control at the operational level. So air pressure, velocity, temperature, given you have a heating system and so on. So there are two ways to control many of these things. And when you are selecting an atomizer, you have to be mindful of what materials you want to produce, what quality you want to produce, because it's normally not possible to make these changes once the atomizer is set. Moving on, yield. So we spoke about this in slightly before. This is what we get out of the atomizer, correct? And this is all the particles that are produced in an atomizer, and this is just what I can use in LPBF, correct? Is there some way I can shift this curve to the left, and that would mean higher yield? This is what we are doing quite a lot. This is what we study a lot. There are several controls which allow us to do it, reducing the diameter of the stream, the nozzle, increasing the air pressure. But all of these come with a constraint that when you do this, you compromise a bit on the morphological aspects. So there's always a fine balance, and you have to find what works for you, for your material. This is very, very sensitive to material tension, surface tension. So different materials will react differently. Somebody asked about circular economy aspect in powders. I think we spoke about plasma spherization. So once you have powder which is used, there are many ways you can reuse this particle depending what is in this particle. So you take a deep look on the particles, what is happening, what is good, what is bad, and you can decide whether just you can reuse it with recertification, whether you can re-spherize it, or you can remelt it. So it depends on what is the powder like. Coming to what to look for in a powder. So when we say powder, it's really a haystack. Really, I mean, this is probably worse. So imagine 1 kilogram of powder and how many individual particles are in it. And if you want to see what bad could happen, just imagine when in AM you're melting maybe 200 micron diameter melt pool, and this would have maybe 4 or 5 particles. And if one of them or two of them are wrong or are problematic particles, you will have a problem because once a crack or something is initiated, it will propagate, it will find its way. So when you want to do quality, or at least when we are doing quality, you really don't want any needle or any wrong or harmful particles in your powder. So it's really like finding a needle in a haystack. And there are two ways to do it. One is qualification, what kind of let's say foreign particles or devil particles are there, and one is quantification, meaning you do it in a statistical manner. So in this talk, or what we are doing internally is in a quantification manner, so we can tell exactly what is there and how much is there and how bad it could be for use. So evaluation, this is basically Um, I think from conventional metallurgy, you probably know this. You always have a tolerance for for defects, and this tolerance will vary depending on what your end use is. If you're making something which just looks nice, like a giveaway at a trade show, you can probably live with a lot of defects. On the other hand, if you're making a tool a die, you want it to run certain number of cycles, 20,000, 200,000, depending on what kind of tool it is. But it is still okay. I mean, let's say it does not run 20,000, it runs 15,000, you can still live with it. At the most crucial stage, if you're making implants, you cannot have any risk here. Or if you're making components that fly a turbine, these are where you really cannot take risks. So the tolerance of defects, of contamination, of whatever will be different from each of these applications. You cannot have one method or one criteria fit all. I mean, you can fit this criteria to everything, but economically it wouldn't work. So different applications logically need different quality standards, and this is what we need to work with the industry. So again, just to give you a feel for what we are talking about, this is what a typical sintering particle would look like, say binder jetting and so on. This is what a typical LPBF laser powder bed fusion particle would look like. And this is what a typical DED or electron beam particle would look like. So if we had to do, if each one of this is one particle, you can see in mass level the difference. And this is what you would appreciate more when we get into contamination topics. So the current methods, the current industry methods for testing of powders is there are many standards. Most of these define various testing related to chemical composition, related to flow, but we really do not have anything that defines particle level purity or contamination. And if you look around, even ASTM or ISO, uh, you get definitions. You get definitions for what is a contamination, what is an impurity, but you don't really have. Unfortunately, we don't really have a defined standard for this. We are working with ASTM on this. We are on the F42 committee, which defines these standards, but it is very hard to use to have something that you use to make it into a standard that everybody can use. That's a big step. So let's see how it goes. But at the moment, there is no ASTM or ISO standard for testing contamination. And this is what we are doing. But again, before we go further, what is a contamination, right? Uh, in this picture, all of this is contamination. The shells in sand, that is not contamination. The rocks, the tiny pebbles, they are not contamination. So contamination is something which is not just non-uniform, but it is also undesired and is harmful. That is contamination. Because there are powders where we intentionally add foreign particles to aid in our manufacturing, to aid in additive manufacturing. That is not a contaminant. A contamination has to be dissimilar, but also disadvantageous or harmful for the process we are using it for. So I found this picture very nice. The shells or the pebbles, they are not contamination. The plastic is. So just so we are on the same page. Uh, this is a self-assembled picture. This is not a real picture, but just gives you an idea of what we are looking for. So you have oxides in powders, you have oxides. You will always have oxides. You cannot really call it a contamination unless it is too much, and then you have a different problem, not contamination. You have morphological difference, so you have powders which are looking very, very different. Maybe, may not be, depending on what we are talking about. Then you have actual contamination. This is something which looks very different, is very different, completely different chemistry, completely different shape, or either and then you may have porosity and so on. You have subgrains, so the nanoparticles or fine particles, part of atomization process. Sometimes it passes through. Now, how do we find the devil particle? How do we find or look for the contamination? Right? There are many methods here. I think somebody asked for non-destructive testing. I don't know how would you call a non-destructive testing in AM, but for powders, but maybe some of these you could be qualified. I mean, you're not always breaking the powder, right? So almost everything you do in a powder is not destructive in that sense. First is visual inspection. I mean, you look at the powder, it looks different, something like this. If you see this, I mean, you have major other problems to worry about. So normally you should not see anything visually. If you're seeing it, you have much bigger problems to deal with, really. Chemical composition, this is good. It gives you a very, very high accuracy. But remember the picture that we talk about, small particles versus large particles. So imagine you have LPPF particles and you have contamination, which are coming from particles which are much smaller, 1 micron, 2 micron, 10 micron. There's a good chance that you will miss it in the chemical analysis. I will show you more accurate examples for this, but because the mass difference is so large, that you might miss them even when there's a big contamination count-wise, you will miss it here. Micro CT, it's very, very expensive. A. B, takes a lot of time and does not give you chemical level data. SEM EDX, so you take SEM, you do spot EDS, expensive, but does give you a very good idea of both morphology and chemistry. And there are methods now which can automate this. So this is what we have chosen simply because you can automate it, and it gives you both chemical and morphological information in one. So again, going back to the atomization cycle, where in this cycle do you think contamination can happen? Raw material would melt down everything you will see in chemical composition. This is where contamination starts. So once you have a powder, once the powder is made, and let's say it is not cleaned properly, and then you atomize something else, you can contaminate. Or at any of the future further stages. So post-processing, sieving, sizing, blending, powder handling. This is once you have the powder at any stage until packaging is where you can have a cross contamination. This could be coming from dust. This could be coming from any other powder that you produce in the same facility and so on. How do we do it? Basically, we use a statistical approach. Did we develop it? No. We didn't have to. Pharmaceutical industry is all powders. Everything pharma starts as a powder, and their contamination can be deadly. So they have the statistics sorted. They know how to test small batches of powder. So getting down from tons of powder, going to ppm of powder, they have their statistics sorted. We borrowed them, the intelligence they had developed, and we implemented the same system that is used in pharmaceutical industry to test for contamination at M4P. The exact test method is different, but the statistical approach is the same. The test method is basically this. You take powder in a stub, you use a tungsten filament SEM, and you do spot EDS. This is the software is written by us. The software basically identifies different particles, different subparticles, satellite particles, different morphologicals, and based on the statistical software, it does a spot EDS on each of these particles. A spot EDS gives you an indication whether this is nickel 718 or 316L. And based on that, you can test at this point at a ppm level, 100 ppm level, the contamination is the powder. Why is it important? I mentioned about count versus volume. Here's an example. We had this from a customer actually. They were getting in their reuse particle, they were seeing more failures. So they sent the powder to us. We saw they had these very tiny cobalt chrome powder in their steel powder. And in the normal chemical composition, you would not see it at all. This is a mass rate, and you don't see anything here. But as soon as you switch to count-based statistics, you see a very strong contamination at the very low end of the PSD. And this was enough. This was enough to have up to 20% increase in failure rate. And this is what they were experiencing and came to us with what's happening with their powder. Uh, Other testing, I will skip through it in the interest of time, but they are all standard ASTM ones. So you will do a elemental test analysis, ICP, OVS wet analysis, ONH, carbon sulfur, SEMEDS is what we spoke about. For PSD, the size, we normally prefer cam sizer. This is the digital image analysis over laser diffraction because cam sizer is more accurate. You are picturing a real particle and all your data is from real pictures and not indirect measurement from diffraction. Flow, the standard Hall and Carney flow. In addition, we do a dynamic flow, which is granulum. So you take powder in this cylinder, you're rotating this cylinder, always increasing the RPM, and we make plots with respect to angle and shape factor. This gives us an idea of how the powder will behave in the machine and over use, how it will change. Then we do moisture analysis. Again, in addition to testing, this is also in addition to ASTM standards or other existing standards. We also do moisture testing for each batch of our powder. Moisture is important because A, it affects the flow, the spreadability. B, it's a source of hydrogen and oxygen, both of which can be very harmful. uh, this is how we test powders internally. Everything that we test is stored digitally and is monitored for statistical process control. Uh, you can ask questions of why it is important. I mean, here I show an example of 316L chromium content can be 16 to 18. This is where we are normally. Question which would you can ask is why do you care? I mean, you could be 16.2 in one batch and 17.9 in the second batch. They're both okay, right? Not really. Remember, I spoke. We are always melting a very small volume in a 200 micron, 150 micron, something like this. Most of these standards were not made for AM. They were made for conventional metals, where volume to surface area ratio is very high. In AM, it's the opposite. Surface area to volume ratio, surface area is very high. And when you look at defects in AM, spatter, balling, keyhole porosity, many of these are driven by surface properties. Problem with surface property is they are very hard to predict, they are very hard to measure, and they are very sensitive to minor changes in alloying elements. So if you have these large changes, with the same process parameters, you will see very large deviations in your printed part property. So even with same powder, same parameter, you will see somehow out of nowhere, in one case, you fail to meet the target tensile property or elongation value. And then this comes into picture. So when you have a very consistent raw material, you get a very consistent produced part property. Same with tap density and so on. So everything is monitored digitally, even the impurity elements, no human has to look at it. If anything is changing drastically, statistical process control, raise an alarm, we can look into it before it goes much too bad. Um, the last topic of the day, new materials. This is an overview of what we have new to offer in terms of aluminum. ALSI10mg is a dark gray one. This is the most well-known aluminum material that you might all know. Then you have strength here, which is basically a more expanded version, better than ALS at NMG in almost everything. Tensile, yield, elongation, high temperature, fatigue, everywhere. Then you have resistale. This is a high temperature aluminum alloy, very, very high temperature strength, not so good elongation. Then you have pure aluminum, 99.9% pure aluminum, basically elongation, very high thermal conductivity. And then you have ALSN 9CU3. This is ADC12, as some of you might know, very standard casting grade alloy, automotive applications. Strength here, as you saw earlier, very high strength, aluminum, magnesium, zirconium, does not need to quench. So you can use it in as printed condition, or you put into a furnace couple of hours at 300 degrees, and you're good to go. So you don't get any thermal stresses. You can print very, very complex shapes, thin walls, and so on. And a very good material for motorsports, for aerospace, wherever you need a 6000 or 7000 series alloys, because those are not printable. This is an AM version, basically for 6000 or 7000 series alloy. Then we have tested it on multiple machines. We have very good data for this. Very, very high fatigue strength, can be anodized. And you see it also different versions of heat treatment is possible. So you can pick and choose between a 6000 and a 7000 series alloy, basically going all the way. This is a use case of this. This is from motorsports. They made this part out of strength hail, achieved a weight reduction of almost 50%. As I was saying, the replacement was from 7075. The conventional part was made out of aluminum 7075, cannot be printed. So we switched to strength hail and achieved all of this weight reduction and so on as a plus. Resistor, again, a very high temperature alloy, very, very corrosion resistant, very good for aerospace, very good for mechanical loaded parts. You see it has really no competition when it comes to high temperature materials. You don't even have to age it or do any sort of heat treatment. Print it, use it, that's it, straightforward. Can be used up to 400 degrees C. Has a very definite fatigue limit, unlike any other aluminum alloy. It has a fatigue limit, so a very prominent fatigue strength. This is not at all common for aluminum. Steels do have a fatigue limit, aluminum alloys do not. This does. Again, you can printing is a challenge for this, so it's not easy to print. CDA has done an amazing job of printing it in a standard SLM machine, one SLM 125. Normally, you need a heated bed, but it's their parameter. We don't have it. But if you have an SLM machine, maybe you can give it a try. We would love to work with you on this. Pure aluminum, names are just pure aluminum, basically very high thermal, very high electrical conductivity, cold plates, and so on. We have a case study of making the cold plate for a Formula E car. Keeps the battery cool, keeps the electronics cool. Again, when you want thermal conductivity, there's nothing you can do better. I mean, you can do pure copper, but pure copper is very hard to print and it's heavy. This is light, this is easy to print, can be printed on any standard machine, basically. Moving to steels, again, we have 316 and 2709. This is maritime steel and stainless steel as base. And then we have add-ons or new materials. So CX Plus, this is corrosion resistant maritime steel. So you see property wise, it's similar to maritime steel with the added advantage of better corrosion resistance and better polishability. You can polish it, you can make it very shiny. One example you can think of is making toolings where you need a very good surface finish, toothbrush and so on, or corrosive plastics and so on. Then you have Fe545. This is a sheet metal alloy. 315S315 for auto bodies. Type 13X, a popular marketing stainless steel C6NM, F6NM for oil and gas industry. CX Plus, as I said, nothing, I mean, property wise, basically think of it as marrying steel, which is stainless and polishable. That is how this material works. So you can make very good tool and dies for medical, automotive, wherever you need a very good finish and corrosion resistance. Here we have an example of knife, something nice to have, but more industrial use cases are there, of course. Then we have 13X. This is martensitic stainless steel, F6NM or CS6NM, very standard material used in oil and gas, industrial power plants. Normally not available in AM, but we have it with process parameters with ready to ship basically. You have a very good fine martensitic microstructure similar to what you would achieve otherwise. So with the added advantage of AM, you can have it also heat treated in the same manner. Some data, you can build it with a relatively normal layer thickness in a standard machine. We have a full heat treatment setup for this as well, so we can support you through and through material process parameter heat treatment. And if you have a target in mind, we can help you reach there. Finally, the sheet metal alloy. This is comparable to S33355. Automotive bodies, prototyping from automotive bodies and so on. This is a use case for this. Our own development, standard chemistry, we have narrowed the chemistry to make it printable. Again, full data is available for standard machines, standard parameter settings, and with the heat treatment. So with this, I would say thank you very much. There's a world of materials in terms of quality, in terms of what you can do, much wider. And we would love to work with you to expand the reach of AM to these new horizons. Don't be limited by available materials. You don't have to be limited by available processes. We can do a lot. The boundary is much too large. And with this, I would say thank you very much.